what we're going to start beginning today and continue with for most of the rest of the course is the wonderful world of carbonyl in its various forms. We have a lot of things going on here. Depending on what's attached, we have a completely different world worth of reactions. Generally speaking, they are, the next two chapters begin with nucleophilic attack here. After that, we're going to deal with substitution adjacent to that as activated because of the electronics of the carbonyl. So just a few basic things before we start. Generally, when I teach part one, the first day of that course, I make sure that people realize there are a couple of things to look for in terms of likely culprits for a reaction site. They are lone pairs of electrons, pi bonds, and polar covalent bonds. Having that mindset, the carbonyl group has all three. We have pairs of electrons on the oxygen. We have a difference in electronegativity between oxygen and carbon, 3.5 versus 2.5, definitively polar in one direction. We have a partial negative charge there, a partial positive charge there, and most importantly, we have the ever-present and usefully weak pi bond, which is, if you remember back to hybridization, a bit of an odd character. The orbitals are parallel, but not head-to-head. Electrons held in a pi bond are inherently easier to get to, especially when pi bond happens to be between non-carbon on at least one side of it. So we have an extraordinarily useful and reactive functional group here, and we're going to use it for almost everything. It comes up virtually every single hour you go looking through the chemical literature. There are reactions that can build virtually any other functional group you want from some variation of a carbonyl group. It essentially has supplanted most other groups as the sort of Swiss Army knife of organic chemistry. If you have this, you can build pretty much anything. We're going to talk a little bit about that. Some of what we're going to do today is background material that is old, things you should have remembered from the past. Some of it will be relatively new stuff. Some of it will be very generic. Some of it will be more detailed. For starters, the first of the chapters we're going to deal with, the aldehydes and ketones, react almost identically. The idea is that a hydrogen here versus a carbon really doesn't make much difference in terms of reactivity. We're going to have two basic types of reactions that happen here, and they could be followed by something else. The first, which we'll see quite a lot today, begins with protonation, or occasionally with a Lewis acid instead of a protic acid with the same effect electronically. If we draw a resonance structure there, we're looking at this. We're looking at a cation on carbon. That look familiar? Where have you seen that before? Forget about the fact that one of them is an O. Where have you seen carbon cations used before? From last semester, roughly halfway through. I know you know which cations are good. You told me that last week. Why did you know that? Where did you learn that tertiary cations are good and that they have hyperconjugation and all that junk? No. The SN2 reaction does not go through a cation. What does? The SN1 reaction. The SN1 reaction goes through a formal cation on carbon. As a result, what do we need as a nucleophile to make an SN1 reaction work? Does it have to be strong and ionic? No. That is a very, very reactive site. It doesn't take much to hit it. We don't need a strong nucleophile if we already have a cation. That's the SN1 reaction. The nucleophile is not part of the rate-limiting step. It's also true here. We're not going to talk about kinetics here, and that 3 should not be readable. We're not going to talk about kinetics here, but the idea is that if we have protonation going on, we're looking at basically an SN1 type intermediate. We don't need that good of a nucleophile. In fact, generally we're going to use this, we're going to be talking about nucleophiles that aren't even negatively charged. That's one. The other case is that instead of bringing in a weak nucleophile, which is what that is, what if we have a strong one? Usually this is negatively charged. Now, we're not going to waste time protonating things to activate them because we have a stronger nucleophile. This is similar but not identical to the SN2 reaction. It is not identical because you are not coming in geometry-wise anti to your leaving group. But in terms of nucleophile strength, they're in the same ballpark. Your leaving group here is a pair of electrons. Your pi bond is acting as a leaving group. So that you have a direct attack on the carbonyl, followed by, or simultaneous with, breakage of that pi bond. If I had money for every time that I have said that in my life, I would be exceptionally wealthy. Nucleophile attacks, carbonyl pi bond breaks, and leaves us with a tetrahedral intermediate shown here. Blah, blah, blah. That should tell you how important it is. If I have to say it every day, that means it probably comes up almost every day. And it does. The same principle exists when we get to esters, acid chlorides, and the like, only at that point we have something instead of a carbon or a hydrogen that could act as a leaving group. So we have a reformation of the carbonyl, and then potentially a second nucleophilic attack. That's the next chapter we're going to talk about. It's not any different, it's just it has a leaving group, so after you can do the addition here, you can have an elimination by kicking a leaving group out to form a carbonyl again, which can then get hit a second time. We'll spend a lot of time on that. Generally, the next step after our strong nucleophile here is afterwards, in the workup, we'll have a dilute acid solution which will act to protonate the oxygen and also act to wash out any leftover metals that are typically attached to the stronger nucleophiles. In terms of what we're going to deal with after that, so this is a nutshell version of most of today and probably half of tomorrow on one board. Part of next week will be if this were a chlorine or an oxygen with another carbon group, it becomes a leaving group. So from here, that first intermediate, we can reform the carbonyl. This is if we had Z as a chlorine or an oxygen or, a couple of other things. And depending on what the nucleophile is, we may, if we get a strong enough one, hit it a second time. That first step, because it involves, after the nucleophilic addition, it involves an elimination, is sometimes called nucleophilic acyl substitution. Like most substitutions, past the SN1 and SN2 chapter, they are not a single step. Just like the aromatic substitution We had to add and then eliminate. Well, the same thing will happen here. We add, then we eliminate internally. Then sometimes we add again. So that is the acid derivatives chapter in a nutshell. This is the aldehydes and ketones chapter in a nutshell. And then afterwards, the chapter after that, we're going to take hydrogens attached to a carbon next to the carbonyl. And we're going to rip them off and exchange them with something because they're next to a carbonyl that is more electronegative, therefore they become more positive. Translation, they're acidic. We can rip them off with a base and replace them with something. So, we're already in 10 minutes talking about changing up one, sometimes two substituents attached to the carbonyl carbon directly, and then building up next door to it. Although actually it's vice versa. If you're going to build up next door to it, you have to do it first. So, what I want you to get in your mind early is that a lot of this is strongly related. There are dozens of reactions in each of these chapters, but they all come down to basically the same principles. The carbonyl has a polarization, it has a pi bond that's weak, we have the ability to attack that. If we don't have a good nucleophile, we need protonation first. That also applies for the acid derivatives. If we do have a good nucleophile, we don't protonate first. We may do it afterwards. We can sometimes take this on to other places, depending on what the reaction is. It still has an OH group. If we wanted to, we could get rid of that. So we have quite a lot we can do, but it's going to come back to the same basic things over and over. So I don't want you to get overwhelmed by the volume of material, because basically they're all going to come down to a very, very small number of possible mechanisms in the end. All right, so now we go old school for a few minutes. Ways of making carbonyls that we already know. This is the cue for audience participation. Ozonolysis of what? Of an alkene. Okay. Problems with that? It'll work. Generally speaking, though, if you were doing a degradation, meaning going to something less complex than where you started, then you probably had something less complex you could have started with. Very rarely is a degradation a method that is of choice. It's handy at times if you can put the right alkene in place, a different method. But generally, if you want to make a carbonyl compound, an aldehyde or a ketone, this would not be the first choice. Unless you're doing something that leaves you with an alkene, like a Diels-Alder, in the right place. Then you would use this. But otherwise, you're simplifying the structure. Generally, there's got to be an easier way. All right, what else? Oxidation of alcohols. We'll talk about that one in a lot more detail. What else do we have back in alkene and alkyne land that led us to aldehydes and ketones? How do I do that? Okay, and that's going to give me what? So if I go through this, I'm going to go through an intermediate of this. Well, not really OH, O minus. That's debatable. But then I get what is a functional group when I'm done, after tautomerization. I get an aldehyde. Specifically, I get an aldehyde that has two hydrogens adjacent to it. So it's a relatively limited method, but still, it is a step up because we can make acetylenes in any form we want, basically from acetylene for the most part. So we can start from something very simple and get to a relatively complex aldehyde in really only 2 steps. An SN2 type substitution and then the hydroboration reaction. Okay, what else? Any other method? Complementary to this from the alkyne. Okay, oxymercuration is going to give me the complementary enol, which after tautomerization is going to give me a methyl ketone from a terminal alkyne. Generally, if you're going to do these from an alkyne, you're not going to use one that's di-substituted because then you don't have control which atom gets the oxygen for the most part. Okay, but still, it gives us a way to get to ketones. Anything else? Friedel-Crafts reaction. Stuff from this semester, okay. However, that only works if we have an aromatic ring. So one of my substituents on the ketone under those conditions has to be aromatic. But that's not a great limitation. There's a lot of examples where that's useful. We have to have the acid chloride to work with, or at least the carboxylic acid. But we can build up to a complex ketone this way. Okay. Anything else? All right, that's a start.